In this video, we're going to learn how to graph a logarithm. We're going to use transformations to do this. So I wrote the how to identify the transformations here on the left, and I'll refer to it as becomes necessary. First, we're going to learn how to graph a parent function logarithm. So very basic, no extra transformations on this graph. We're going to graph log base 3 of x to get an idea of what these graphs look like. Now, a way to find numbers to plug into a logarithm is actually helpful if you change your logarithmic equation into an exponential one, meaning that the log is equal to the exponent you raise 3 to get x. So 3 to the y power is equal to x, and much different than the other functions we've come across, we'll actually pick the y values to plug in to get the x values. It'll make the process a lot easier and more smooth to get through. So we're going to pick numbers for y, like -2, -1, 0, 1, and 2. And by plugging them into the exponential form, we'll figure out what the x values are that go with it. Meaning if I plug those x values into this log, it would give me the following y value. So here, if I plug in, I'm actually going to start with 3 to the 0, since it seems to be a nice central point. And 3 to the 0 power, in fact, any number to the 0 power, is 1. And usually with your parent function, you can count on getting y is equal to 0 and x is equal to 1 if you strip away all transformations. Now, if I continue onward to 1, 3 to the first power is equal to 3. So x will equal 3 when y is 1. And then 3 to the second power is equal to 9, so x will equal 9 when y is 2. If I move backwards, I'll have 3 to the -1. Since that's the negative exponent, it can move to the denominator, so 3 over 1 to the first, 1 over 3 to the first is 1/3. So when x is 1/3, y is -1. And for 3 to the -2, that's also known as 1 over 3 squared, which is 1/9. So when x is 1/9, y is -2. And you'll see how quick that process was when we used the exponential form rather than the logarithmic form to find points. Now, plotting all of these points, when x is 1, y is 0. When x is 3, y is 1. And when x is 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, y is 2. I'll have this kind of upwards traveling graph, but it just travels upward very slowly on that curve. Now, when x is 1/3, y is -1. And when x is 1/9, even closer to the y-axis, y is -2. So you're going to notice it's going to flatten up against this curve. Since exponential functions can't equal negative numbers, we'll never get a negative x or a 0. So the graph actually flattens up near, but never touching, the y-axis, and then curves, and just slowly curves upwards. And it does continue to grow upwards. It just goes up slower and slower over time, but always growing bigger. So one thing you'll notice here is that since it never touches the y-axis, that makes the y-axis an asymptote. Now in this case, the asymptote isn't horizontal like an exponential function, it is vertical. So I'll have a vertical asymptote for this function at x equals 0, which is also known as the y-axis. Now, a few other key things change as well. The domain for this function is not all real numbers like an exponential function. It's actually cut off at 0, so the domain is 0 to infinity or x is greater than 0. And the range for an exponential function was 0 to infinity typically, but you're going to see here that the range is all real numbers because it will continue to grow and it will get as low as you need it to be. So the range is -infinity to infinity or all real numbers. So it looked like the domain and range switch, which is the key notion of an inverse function. So you'll notice that logarithms are inverses to exponential functions. You can kind of see it in the graph as well. So now let's talk about graph and logarithmic function when it has these transformations. So we'll see here we have log base 4 of x minus 3 plus 4. Now since I'm subtracting directly from x, that's going to correspond to a horizontal translation. And since I'm subtracting 3, that means I go right 3. And the plus 4 on the outside corresponds to a vertical translation. And plus 4 means up 4. So now that I know how the function's transformed, we're actually going to look at the parent function first. And then we'll find the actual function. So the parent function is log base 4 of x, but I'm going to use this exponential form. 4 to the y is equal to x to find points. So we'll use -2, -1, 0, 1, and 2 for y to help us find the x's that go with those. So plug it in 0 in for y, I get 4 to the 0, which is 1. So x is 1, y is 0. You'll see that as a common point with these parent graphs. And then plug it in -1, I get 1 over 4 to the first, which is known as 1/4. So when x is 1/4, y is -1. And for 4 to the -2, it's known as 1 over 4 squared. It's 1/16. So when x is 1/16, y is -2. Now when I plug in 1, I get 4 to the first power. It's giving me 4. So when x is 4, y is 1 for log base 4 of x. And when y is 2, x is 16. Now let's go ahead and plot these points. And I'm going to plot them in green in a dashed line so it doesn't stick out too much. So we have 4 is 0. Oh, sorry. 1, 0. So 1's over here. 4, 1. You'll see I'm counting by 2's on my axes. So 1 is actually in between 0 and 2. And then 16, 2. And then 1/4, which is up against the side here, -1. And then 1/16, -2. So you'll notice when I go to graph this, I'm going to make it a dashed line because this is not my final graph. It squeezes up against the y-axis, and now we're going to apply the transformations for my final graph. Every point is going to shift up 4 and right 3. So this point that's here at 16, 2 is going to go up 4, so it's 2, 4, and then right 3, so 2 and then 3. And every point's going to follow that pattern. So the one here at 4, 1 is going to go up 4 to 5, and then right 3 from 4 to 7. The point here at 1, 0 is going to go up 4 to 4, then right 3 to 4 as well. And then you'll have those points are hugged up against an asymptote, which is normally at x equals 0, but since I've shifted right, that asymptote has moved over from 0, 3 to the right, to x equals 3. Because I've shifted my graph to the right, it goes from 0 to 3. And those points over at 1/4, -1, will be at now 1/4 plus 3, +1, and so on. And our graph will squeeze up against that asymptote curve and go upwards very slowly. So if I were to analyze this graph, its domain doesn't go from 0 to infinity anymore since I've shifted to the right, and now it goes from 3 to infinity because it starts at the asymptote 3 and goes to the right, but you do not include 3 because it never actually reaches that number. The range is still all real numbers, so negative infinity to positive infinity, and our vertical asymptote is x equals 3 since it shifted over 3 units. Now let's look at y is equal to 3 log base 2 of negative x. Now we're going to graph the parent function, y is equal to log base 2 of x, but its exponential form is 2 to the y is equal to x. So we'll pick those same values for y, so negative 2, negative 1, 0, 1, and 2. Plug it in 0, get 2 to the 0, which is 1. So when x is 1, y is 0. 2 to the negative 1 gives me 1 over 2 to the first, so 1/2. And 2 to the negative 2 will equal 1 over 2 squared, which is 1/4. So when x is 1/4, y is negative 2. So 2 to the first is 2. So when x is 2, y is 1. And for 2 to the second, that's 4. So when x is 4, y is 2. And I'm going to plot this very lightly in green. So when x is 1, y is 0. Here I'm counting by ones again. When x is 2, y is 1. And when x is 4, y is 2. And then when x is 1/2, y is negative 1. And when x is 1/4, y is negative 2. So here's what my logarithm looks like. You'll notice the smaller the base is, the more it looks like it's growing. But when you have a bigger base, it almost looks like it flattens out very quickly. It stops growing as quicker. Now let's apply these transformations. So first, I'm going to look at the negative x on the inside. That is a reflection in the, when negative's on the inside, the y-axis. And then the 3 out in front is a vertical stretch because that value of 3 is bigger than 1. So a vertical stretch by a factor of 3. So to plot this, I'm first going to reflect it across the y-axis. So every point will be reflected across the y-axis. So look very symmetric here. And then I'm going to vertically stretch the graph, which means I'm going to multiply all of the y values by 3. So the point here that's at negative 4, 2. 2 times 3 is 6, so it's going to be at negative 4, 1, 2, 3, 4, 5, 6. The point at negative 2, 1, when multiplied by 3, is now at negative 2, 1, 2, 3. The point here at negative 1, 0, 0 times 3 keeps it at 0. The point here at 1/2, negative 1, when that negative 1 is multiplied by 3, goes all the way down to negative 3. And the point here at 1/4, negative 2, when that negative 2 is multiplied by 3, it goes all the way down to negative 6. So now you can definitely see it's definitely growing up and to the left over there. But we'll still have the same vertical asymptote. It looks like it's still along the y-axis. So my vertical asymptote is still x equals 0, the y-axis. The domain, this time, instead of going from 0 to infinity, actually goes from negative infinity to 0, or x is less than 0. while this one over here was x is greater than 3. And the range is still all real numbers, negative infinity to positive infinity. And that is how you graph a logarithm.